Alright guys, welcome to lesson 7.5. Today we'll be talking about graphing functions that look like this. These are called inverse variation functions. And what they are is they're a basic type of rational expression. So I want to focus on graphing these today. And the reason I want to do that is because it's going to lay the groundwork for some concepts that will come in handy when we're talking about graphing more complicated looking types of rational expressions, like a basic rational expression, and it will help us develop some ideas to graph some more complicated ones in future lessons. And those ideas that we'll be looking at are things like how to describe in behavior with limit notation, and also how to use limit notation to describe what happens at the vertical asymptote. And we'll also identify where the asymptotes are located. So it's basically just a preliminary lesson for some stuff that we'll be getting into a little bit later. So let's go ahead and jump in and get started. So the first thing I would like you to do is I'd like you to complete this table and graph. And then when you're all done, we'll compare our answers. I'll do the first part for you. So for instance, if x equals -2, you're going to plug -2 into your function. 1 divided by -2 is -0.5. And so then you're going to plot that point on your graph. -2 and -0.5 would be located approximately right here on the graph. Okay, so go ahead and pause the video here, and on your notes, go ahead and complete the table on your own and plot the dots. And when you're all done, we'll compare our answers. By the way, do not connect your dots yet, because something a little strange will happen along the way. So, but go ahead and finish it, and when you unpause the video, you'll see the final answer. All right, so your end result should have looked like this. Now, you might have noticed something odd happening here at 0. When you plug in 0, you can't have 0 in the denominator. That's undefined. So you don't get, I'm concerned if you guys were doing mental math, you might have put 0 here by accident, but 1 divided by 0 is not 0. It actually doesn't exist. There's no answer there. And so what that means is our function doesn't exist at this point. And the reason for that is because if we do connect these dots, your graph will actually look like this. If we found a bunch more dots, it would look something like this. Okay, and so now you guys can connect your dots. And so basically what happens is that this graph is not reaching the value 0. We can get closer and closer to 0, but it will never actually get there. So you could plug in something even closer to 0 than 0.5. You could plug in 0.25, or you could plug in 0.025, or you could plug in 0.000001, and you'll keep getting answers, but what you'll never get is an answer if you try to plug in 0. You can get really close to 0, but you can never get to 0. Okay? All right, so let's do another one of these, but this time you'll notice that the bottom is squared. Okay? Go ahead and pause the video here, plug in these numbers for x, square them, and see what you get, and then plot your results. When you unpause the video, you'll see the solution. All right, and so here's the result. Now, if you were to continue to plot more points and connect the dots, what you're going to find is that it kind of something like this. Okay, and the reason it looks like that is because of this even power. The even power cancels the negatives out. So instead of getting a graph down here where all the y values are negative, when you square the negative x value on the left side, that's negative, that's where the x's are negative. When you plug in a negative x value, you end up getting a positive y value, so it ends up being up here, just like it is on the other side. So you end up with this symmetrical looking shape here. And so they have a very similar shape, the one from the last slide and the one from this one. But whenever you have an even power, instead of getting the left side being down here in the bottom, the left side is also on the top because everything becomes positive. the result of. And so to help you guys understand these concepts a little bit, I'm going to be making use of the Desmos.com. It's kind of helpful for a lot of things. So we'll be using it quite a bit today. Can you bring that up? All right. So let's go ahead and put the function in there that we were graphing. We were graphing the function f of x is equal to 1 over x. There it is, right? And what we found was we found this point here where x is equal to -2. Plot these points. -2 was -0.5, right? We also found the point -1,1. And so on. But as you guys know, that there's really an infinite number of points on this graph. These are just the 3 that we found. But just to kind of demonstrate a few things to you guys, as you can see, this graph gets closer and closer to x equals 0. So right now my x value is 0.173, but it'll never let us fully get there. I can go all the way up here, and it's still not at x equals 0. It will never let me get there because the function doesn't exist. And the closer I get to 0, the higher and higher the function seems to climb. Okay. The same thing happens on this side. If you try to get closer to 0 on the left side here, -0.152 is pretty close to 0. No matter how far down you go, you're just going to get closer to 0, but you'll never be able to get there because once again, the function doesn't actually exist at 0. And so what we end up with is a vertical asymptote at x equals 0. So I'll go ahead and plot that. I'll plot it there with a dotted green line. So that dotted green line represents a vertical asymptote that this function will never reach. Now, another thing happens as we go to the right forever. As you can see, as we go to the right, I can let x get bigger and bigger. Like here, it's 11, x is 11, and my y value is really close to 0. It's like 0.089. But even if I let x get really, really big and I slide all the way out here to like where x is 76, my y value still isn't 0, and in fact, it will never get there. So in the same way, we also have a horizontal asymptote. And I will put one of those on there at y equals 0. Same thing happens on the other side of the graph as well. We'll represent that with a dotted line as well. So the purple dotted line there represents my horizontal asymptote, and my green dotted line represents my vertical asymptote. And what an asymptote is it basically just is a value represented by these lines that the graph can get closer and closer to, but it will never actually reach it. So that brings us to our definition of an asymptote. An asymptote is a value, usually represented by a line on a graph, that a function approaches but never reaches. Okay? So let's go back to Desmos for another demonstration. I'm going to get rid of all these dots. We don't really need these for the next demonstration. But what I do have on here is I have my, my graph, and I also have my vertical and horizontal asymptotes. Now, as you guys remember, if you ever add a number to your function, what happens to your function? Like, let's say I add 2 to my function. It shifted the graph upwards, right? And now that means that my horizontal asymptote is no longer at 0, but now it's at 2. So however much you add to your function, that will shift your graph up, and it will change your horizontal asymptote, represented by this purple dotted line, to be whatever that value is. Another thing that you can do is you can also set it back to where it was really quick. If you subtract a number from your function, say I subtract 4 from my function, now my graph has been shifted down, and now my horizontal asymptote is down here at -4. Okay, so we've learned before that when we're doing transformations, if you add a number to your function or subtract a number from your function, that shifts it up and down. And in the case of these functions, that number you add or subtract basically tells you where your horizontal asymptote is going to be located. All right, so let's reset it back to where it was. Now, what if instead of adding or subtracting a number to the function, you just add or subtract a number to the x? Let's say I subtract a number from x, like -5. Well, now my graph has been shifted over, and my green horizontal asymptote, which was originally here at 0, is now going to be shifted over to 5. Okay, so we also remember from our unit on transformations that when you subtract a number from x, that shifts your graph to the right. So your vertical asymptote will be the opposite sign of whatever number you have here next to the x. So since I have a -5, that shifts my graph to the right, and therefore my vertical asymptote will be at 5. And if I were to add 5 instead, the opposite happens. That shifts the graph to the left, which means that now my vertical asymptote is -5. Okay? And so all I'm doing is I'm showing you two things. We're reviewing transformations, but also at the same time, I want you guys to see that whatever number you're adding or subtracting from the x will help you know what your vertical asymptote is. And whatever number you add or subtract to the function will tell you what your horizontal asymptote is. Okay? So let's go ahead and summarize that in some notes. Actually, before we summarize that, I wanted to talk about one more thing. Let me set it back to the way it was. All right. Now, what happens if you multiply your function by a number? So if I multiply this function by 2, well, 2 times 1 over x, that's just like the number goes in the top. So we'll just put it in the top. It didn't really change it, right? Compare this to the original. They're pretty much the same. I'll switch it back and forth. Watch. 1, 2. 1, 2. There's barely a difference. Now, if I make it a really big number, like 10, you'll see a little bit more of a difference. And what that does is it stretches or compresses the function. Now, honestly, I don't really care. We're not going to talk about stretches or compressions on these functions. That's not important. But what we will talk about is reflections. If you multiply this function by a negative, it flips it upside down. Right? I want you guys to be aware of that as well. And so after all those demonstrations, hopefully we've laid a good enough groundwork for you guys to be able to understand some of the basics that we'll be needing when it comes to graphing these inverse variations. Okay. So first of all, what we learned is that whatever number you're subtracting from the x, that's going to tell you what your horizontal asymptote is. I'm sorry, your vertical asymptote, my bad. And whatever number you are adding or subtracting from your total function will tell you what your horizontal asymptote is. We also saw earlier that whenever you are graphing these functions, we saw what they look like. They look like this, right? But that's if they had a positive a value on the top and an odd power. We also saw what happened if we had the power even. When you had an even power, both halves of the graph were on top. Okay? And finally, what we've also saw with our exploration of these functions is we've seen that if you make the fraction negative, it flips it upside down. And that's an old topic. That's a transformation known as a reflection, which we talked about. So if you have an even power, but you make your fraction negative, it's going to flip that shape upside down, so it will look like this. And if you have an odd power, it will flip this shape upside down, which will make it look like this. Okay, and so this is one of our most important slides for the day that will help you know how to graph these functions. All right, so for example 1, what we're going to do is we're going to practice just graphing these inverse variations, these basic rational expressions. So Go ahead and begin. So the first thing you're going to want to do, y-axis, the first thing you're going to want to do is you're going to want to graph your horizontal and vertical asymptotes. So whatever number is right here, we're going to take the opposite of that number, and that is going to be my vertical asymptote. So my vertical asymptote will be x equals a positive 3. You do the opposite sign, just like we've always done with transformation. So I'm going to draw a vertical line at x equals 3. So 1, 2, 3, and a little vertical line right there. Next, whatever number is right here, that tells me what my horizontal asymptote is going to be. So my horizontal asymptote in this case is going to be y equals. So I'm going to draw a dotted horizontal line going through y equals 1. Now, basically, then I have 4 shapes that I need to choose from. Here are my 4 options. Okay. Now, let's take a look and see which shape it's going to be. I have a positive fraction, and my power is odd. So I've got a positive fraction and an odd power. So I'm going to be graphing my graph to look like this. So my final answer then will look something like this. That's it. That's the end of number 1. So step 1 is to identify your vertical asymptote. It's the number next to the x. Step 2 is to identify your horizontal asymptote. It's the number that's out here. Step 3 is to pick the correct shape based on whether your fraction is positive or negative and whether the exponent on the bottom is even or odd. So let's go ahead and take a look at the next one. Number 2. All right. So what is the vertical asymptote for this function? Vertical asymptote is the opposite of whatever number is next to the x. So in this case, my vertical asymptote is going to be -2. And so I'm going to draw a vertical line at -2, the x-axis. Next, I want to identify my horizontal asymptote. That's this number here. So my horizontal asymptote is going to be the line y equals -3. I'm going to go down 3 spaces on the y-axis, and we're going to draw a green dotted line to represent that. The final thing I need to do is I need to pick the correct shape. Now in this case, I've got an even power down here. It's squared, but I still have a positive fraction. So I'm going to look at my little chart here. And I'm looking for the shape that has a positive fraction, but an even power. And so in this case, it will look like this. So I'm going to be connecting these dots. Or not connecting these dots, but I'm going to be sketching my shape to look like that. So it'll be up over here and also be that on this as well. There's the graph of that function. All right, let's do one more to kind of get it really embedded in our minds there. All right. Now, if you're ever missing an h or a k, guess what? You're going to do the same thing that we've always done if you're missing an h or a k. There's 0. So in this case, since there's no number being subtracted from the x, we can rewrite it like this. That means the h is 0. And the same thing applies if you don't have a number out here. If there's no number out here where the k is located, that would be 0. All right. But that means that my vertical asymptote in this case will be 0. My horizontal asymptote will be 1. So let's go ahead and graph those first. If you have a vertical asymptote at 0, that's just going to be basically the y-axis equals 0. And if we have a horizontal asymptote at 1, finally, we're going to use our little chart to determine what shape is the correct shape. So, on this particular problem, my fraction is negative and my power is even. Oh, actually, this was supposed to be a 4, wasn't it? Doesn't matter, it's still even. So I've got a negative fraction with an even power, and therefore I will be using this shape. And so when I sketch my graph, like this. There you have it. Okay. So I'll let you guys go ahead and pause the video and try some example problems here. Let me bring them up first. Here's some for you. When you unpause the video, I will have the graphs available for you to check your work with. All right, so here's the answers. For number 1, you should have had a vertical asymptote at -3 and a horizontal asymptote at -1. And since we have a positive fraction with an odd power, your curves would be in the top right quadrant and the bottom left quadrant of those asymptotes. For number 2, we would have a vertical asymptote of 1. And since there's no k value here, that would be a horizontal asymptote of 0. So right here at the x-axis. And since, once again, there's no power on here, we can assume that's a 1. And so we have a positive fraction with an odd power, which means, once again, just like number 1, the pieces of our curve will be in the top right quadrant and the bottom left quadrant of our asymptotes. Finally, on number 3, we have no h value, which means that h is 0. Therefore, my vertical asymptote will be the y-axis. My k value is 2, so my horizontal asymptote is 2. And since I have a negative fraction with an even power, that would be this shape here, upside down on both sides, bottom left and bottom right quadrants of the. And that's how you graph these types of functions. So let's do another Desmos demonstration. So here's our graph that we've been looking at. We could also do the one where you have an even exponent, focusing on the one with odd exponents. So let's take a look at this one really quick. Now, as you guys can see here, as I go to the right, the y value gets closer and closer to 0, but it will never actually get there. Now I think this thing actually says y equals 0, but it never really actually gets there. It just gets closer and closer to 0. There we go. I think it says 0. I'll get rid of that. As you guys can see, no matter how far to the right I can go way out here, like where x equals 155, and, well, it says 0, but that's probably because the computer can't calculate it at that low of a value. But it should technically never be reaching 0. So it just keeps getting closer and closer. So it looks like the computer kind of gives up. Heck, it's 0. It's so close. But it actually isn't. It never really gets there. And so as x gets bigger and bigger and bigger, in other words, as x goes off into infinity, the graph gets closer and closer and closer to 0. And the same thing happens on both sides of this graph. As I go this way, as x gets farther and farther out towards negative infinity, the y value gets closer and closer to 0 on that side as well. Okay? Now that should be ringing a bell with some vocabulary that we've learned earlier, and that's limit notation. Let's review limit notation really quick, and then we'll talk about how we can use limit notation to talk about the end behavior of these functions. So what does this mean? This means that as x approaches c, so as x approaches c, and that's what that little symbol right there means. As x approaches c, y approaches k. And that's represented right here. F of x is y, so f of x now says equals k, but what it really means is that even though it never gets there, it's approaching k. So as x approaches c, y approaches k. That's how we read this statement. So now let's talk about the end behavior of these graphs. It doesn't really matter if you're talking about the right end of your graph or the left end of your graph with these functions. On the right end of our graph, we say that x is approaching positive infinity. So that's over here on this side. I'll highlight that there in red. As x approaches infinity, the y value, represented by our function here, gets closer and closer to the horizontal asymptote, which in this case we'll say is k. So as x approaches infinity, the function approaches its horizontal asymptote of k. It gets closer and closer to that. Now on our graphs that we've been looking at, it's always been 0. But that's just because the graphs I've been using have the same horizontal asymptote. The point is that it gets closer and closer to that dotted line. So that dotted line is the horizontal asymptote, which is represented by k. The same thing happens with your left end of your graph. That's where x is approaching negative infinity. On the left end of my graph, which is over here, we're also approaching k. So it doesn't matter whether you're approaching x approaches infinity or negative infinity. On either side of your graph, you're approaching the same y value of k, which is your horizontal asymptote. Okay, so that's the end behavior of a inverse variation. So, for example 2, I want us to describe the end behavior of these functions. So how do we describe end behavior? Well, let's go ahead and, instead of writing out this entire function here in this spot, let's go ahead and just put what it equals. We'll just put y there. It's a little bit less writing. So the limit of this function as x approaches infinity. Now this is the right side of the graph because that's a positive infinity. What does it equal? Well, it just equals its horizontal asymptote, which is 1. And on the left side of our graph, in other words, where x approaches negative infinity, it's also 1. Now, before I move on to number 2, I just want to demonstrate that once again using Desmos real quick, and then we'll do number 2. So let's put that new function in there. The new function we're working with is 4 over x minus 3 plus 1. That. Now, as you guys can see, as x goes to the right forever, my y value gets closer and closer to 1 because that's where the horizontal asymptote is now, because it's been shifted up by that plus 1. The same thing happens on the left side as x gets more and more to the left, a negative value, the y value gets closer and closer to 1 on this side also. By the time you're way out here, it's still getting closer and closer to 1. It will never actually get there. And so just wanted to make that re-emphasis there using the graph. Let's take a look at number 2. So for number 2, if I want to describe the end behavior of this function, this is how I would do it. The right end of my graph is represented by this as x approaches positive infinity. And the y value that we're reaching is whatever the horizontal asymptote is. So as x goes to negative infinity, y approaches -3. And the same thing will happen on the left side of my graph, represented by this negative infinity. As x approaches negative infinity, the y value also approaches -3. All right, let's take a look at number 3. Once again, we're going to do our end behavior on the right side. And we're also going to do our end behavior on the left side of the graph. And on both sides, the end behavior is equal to whatever your horizontal asymptote is. That's the value that it's getting closer and closer to. Okay? And so that's how you describe the end behavior of one of these rational functions here. All right? Why don't you guys go ahead and pause the video and try student practice number 2. When you unpause the video, you'll see the solution. Okay, and so here's the solutions for the end behavior of each one of these functions. The only one that might have been a little tricky is number 2, because they didn't actually have the k value, but as we've mentioned, when there's no k value, that means it is 0. So there is the end behavior for each of these functions. And what this does is it just tells us basically at the extreme right and left end of the graph that the y value gets closer and closer to this number, which is our horizontal asymptote. All right, guys, let's do one more Desmos demonstration. Kind of already talked about it, honestly, but we're going to get into a little more detail on it now. So what we've done so far when we've talked about limit notation, we've only talked about going off into infinity, which means to the right forever or to the left forever. But you can also use limits to approach other things. So in this case, with this graph here, I'm going to approach this blue line. So I'm going to start on my graph of 1 over x, and I'm going to approach the blue line from the right. Now, as I try to get closer and closer, it's like there's an invisible force field there. It won't let me get there. It keeps pushing it up. No matter how much closer I try to get, it just keeps pushing the graph up higher and higher. It won't actually let it touch that blue line. And as you can see, we zoom in, and it just never really gets there. Really high. But the point is as we approach the blue line from the right side, no matter how close we get to the blue line, we'll never get there. And as we do, it just keeps pushing that y value up higher and higher and higher. Okay, and so what we can deduce from that then is that as I approach the blue line from the right side, my graph goes up into positive infinity. So we could write it out like this. My function, I'm approaching that function, I'm approaching an x value of 0. I'm trying to get to where x equals 0. It won't let me, but I'm trying to. And I'm approaching it from the right side. Now here's how we say that we're approaching it from the right side. We put a little plus. Plus means right. As I approach 0 from the right, the graph just goes higher and higher up into infinity. Okay, so that's for this situation up here. Now what about down here? On this side, I would be approaching the blue line from the left side. But as I get closer and closer, it pushes the graph down into negative infinity. So the way you would write that is the limit of your function as x is trying to reach 0 from the left side. We use a minus now to represent the left side. So as I'm trying to approach 0 from the left side, the graph gets pushed down into a y value of negative infinity. The y values keep going down farther and farther and farther as we get closer and closer to 0. Okay? So, let's go back to our notes. So, these are what we call one-sided limits. Okay, when you have a little negative right here after the number, that means that x is approaching h, but it's approaching it from the left side. And the h represents the number where our vertical asymptote is located. So as we are approaching the vertical asymptote from the left side, that's what this indicates. here. And for this one, if I'm approaching my vertical asymptote from the right side, this is how we would write it. We would put the h, which represents the asymptote, with a little plus after it. Okay. Now, let's put all this in a table. So earlier we looked at some graphs, and they looked like this. And the shapes of these graphs are based on two things. They're based on whether the power is even or odd. If the powers are even, they're both going up or they're both going down. If the powers are odd, they go in opposite directions on both sides. And based on whether the A is positive or negative, you get these different directions because it's a vertical reflection. And so what I have written now, this is the same graph chart that I gave you as earlier, but now I've got some limit notation in here to describe what happens whenever you are approaching the vertical asymptote. So here, the H represents the vertical asymptote. All right. And this one is saying I'm approaching the asymptote from the left, so that's this side. And as you can see, as I approach it from the left, the graph goes up. And as I approach the asymptote from the right, the graph goes up. So we're going to put infinity on both of these. For this one down here, whether you're approaching from the left or the right, either way, the graph goes down into negative infinity. The y values go down into negative infinity. Now over here, on the left side, it goes down into negative infinity. But on the right side, it goes up into positive infinity. So they do opposite directions. And for this one, on the left side, it goes up. And on the right side, it goes down. So this is how we describe the behavior of these functions at a vertical asymptote. They have infinite limits. The limits are infinities. And the direction they're going is based on what kind of graph we're looking at. And the type of graph we're looking at is based on the power and whether or not your fraction is positive or negative. All right. Let's go ahead and see if we could describe the infinite limits at the vertical asymptotes for our functions. All right, so example 3. First of all, we have to decide what kind of a shape this graph is going to have. So I have an odd power here, and it's a positive fraction. Now, when you have an odd power with a positive fraction, that means we are going to have this situation. My graph would look like this. So that would mean that on the left side of my asymptote, it's going down into negative infinity, and on the right side of my asymptote, it's going up into positive infinity. Okay, so we need to write our answer out now. Let's do that really quick. So what we're going to do is we're going to say the limit as x approaches my vertical asymptote, which is 3 in this case. For this function, we'll call it y. On the left side, it goes down into negative infinity. So I'm going to put a little negative here after my 3. And on the left side, it goes down to negative infinity. And on the right side of my asymptote, so I'll put 3 with a plus to represent the right side of my asymptote, it goes up into positive infinity. So that's the answer to number 1 there. Now in number 2, we have a even power and a positive fraction. And when you have that kind of a situation, it's up on the left and it's up on the right of that vertical asymptote. So how would we write this? We would say, okay, the limit as x approaches the vertical asymptote, in this case that's a -2. On the left side it goes up, so I'm going to put negative here for indicating that we're on the left side. And to indicate that it goes up forever, we're going to put positive infinity. Then, to describe what's happening on the right side, I'm going to write my vertical asymptote here with a plus to indicate we're on the right side. And then what happens on the right side? It's also going up. So positive infinity. So whatever you're putting over here indicates whether it's going up or down. And whatever you're putting here, if it's a plus or if it's a minus after the number, that's indicating left or right. So pretty much it. Let's take a look at one more here. In this case, I have an even power with a negative fraction. When you have an even power and a negative fraction, your graph looks like this. It goes down on the left and it goes down on the right. In this case, my vertical asymptote is 0. So here's how I would describe what happens with my function as it approaches the vertical asymptote. I would say the limit as x approaches the vertical asymptote, which is 0, from the left side is, well, what's happening on the left side? Is it going up or down? It's going down, so I'll put negative infinity. And then to describe what's happening on the right side of my graph, I'm going to put x is approaching my vertical asymptote. On the right side of my graph, that's where I'm going to put a little plus here after the 0. And on the left side, it's also going down, so it's negative infinity here as well. Okay, and so that's how we use limit notation to describe the behavior of a function as we approach a vertical asymptote. Okay, so why don't you guys try this one here. Pause the video, and when you unpause it, you'll see the solution. Okay, so here are the solutions. My vertical asymptote number 1 is negative 3. And so as we approach from the right side of the graph, it would be going up. And as we approach negative 3 from the left, the graph goes down. And that's because the shape looks like this. Up on the left side of the asymptote and down on the, I'm sorry, I think I said that wrong. Up on the right side of the asymptote and it's down on the left side of the asymptote. All right. As for the next one, it's actually the same. My asymptote is 1 though this time. So as I approach 1 from the right, it's up. And as I approach 1 from the left, it's down. And that's because the shape is the same. On the right side of my vertical asymptote of 1, it goes up. And on the left side of my vertical asymptote, it goes down. Then finally on number 3, the vertical asymptote is 0. So if I approach 0 from the right, it's negative infinity. And if I approach 0 from the left, it's also negative infinity. And the reason for that is because this is a even powered function with a negative. And so this graph looks like this. It's down on the left and it's down on the right. So whether you're approaching 0 from the right or from the left, either way, you get negative infinity because it's down on both sides. Okay? And so that's how we describe, once again, the behavior of a function at the vertical asymptote using limit notation. And that concludes our lesson for the day. So we'll see you guys next time.